רגע, שאני אצייר את המצלמה. אני לא יודע, אני צריך לראות איך הקורס יתקדם. אם יהיה ביקוש, אולי נעשה משהו, אולי אתה יכול, מי ביקש את זה? אולי אתה יכול לתת איזושהי... לא, למה המצלמה מחוברת? שנייה. רגע. כן, בקיצור זה...
איפה יש על זה בכלל שאפשר לקרוא, לראות?
אוקיי, יש כל מיני כיוונים לכל מיני דברים, אפילו יש איזו תוצאה שלי, של קולגות, משהו לגבי להיות אנליטיות, שאנחנו בעצם לפתור שם איזושהי בעיה ולהבין משהו שקורה פשוט בעולם קומוטטיבי, דווקא באמצעות תופעות לא קומוטטיביות. אני יכול, כאילו, in a nutshell,
כי כאילו כל הדברים פה הם מאוד אבסטרקטיים, ואני חושב איפה אני יכול נגיד ליישם אותם, ולי אין מושג, אז המנחה שלי במקרה סיפר לי על זה.
זה הולך הרבה, באמת, זה מגיע למגוון תחומים. אז גם סתם, בוא נגיד, תדרוק לך משהו ככה סתם לך. אז נגיד אם אנחנו מדברים על יריבות, ואז זה המורכבים. למשל, אז יש לנו, אוקיי, אז נגיד שאני מסתכל על יריעה אלגברית, אז נגיד מסתכל על היריעה, משתנה אחד.
אוקיי.
אוקיי? שנוצרת על ידי הפולינום x בריבוע. אז רק 0 מתבצע על x בריבוע, ולכן התחילה רק הנקודה 0, נכון? ולמעשה, היריעה שנוצרת על ידי הפולינום x בחמישית, והיריעה שנוצרת על ידי x בריבוע, נראות אותו דבר. צריך לעבור רדיקלים כדי לקבל ניסיון של אינברקים. אבל ברגע שאני יכול להתחיל לשים דברים מאלגבראות סיפוחת, למשל מטריצות, אז פתאום המטריצה 0,1,0,0 היא 0 של הפולינום x בריבוע, ולא של הפולינום x. אז ברגע שאני מאפשר כניסה לתוך, זאת אומרת שבכניסות של הדברים יהיה לך דברים לא קומוטטיביים, בעצם צריך שיהיו שם, בסופו של דבר אתה כן יכול להישאר עם פולינומים קומוטטיביים, או עם פונקציות קומוטטיביים.
ואתה עובר לפולינומים על אלגברה גדולה יותר,
בדיוק, ואז פתאום משפטים, או לא רק משפטים, אפילו בעיה פתוחה, שאתה אומר, יש פה איזושהי בעיה. אני לא יודע לפתור אותה, קשה לי לעבור, הבעיה היא ברורה לחלוטין במקרה קומוטטיבי, אני יודע לנסח אותה במשפט. אבל אם אני רגע עובר למקרה לא קומוטטיבי, וכיוון שיש לי פתאום התאמה יותר מסודרת, התאמה one to one כזאת, פתאום אני יכול לדבר על האספים של הפולינום, הנה, אז פתאום כזה דבר נהיה, מאפשר לך לפתור את זה. עכשיו, אתה יכול להגיד גם לדברים כאילו אנליטיים, לאינסוף ממדיים, באמצעות שימושים קונספטיים כאלה. ואז זה פותר בעיות, מה שיכול לפתור לך בעיות קומוטטיביות, שבסופו של דבר אתה תנסח אותם.
אקטיבית לגמרי, אבל
תעבור בדרך משהו כזה. וזה יפה, בכיף שזה קורה. טוב. אז זהו, שבינתיים אנחנו כן לומדים כלים, ואתה יודע, ואבסטרקטיזציה. אולי נזכיר מה עשינו, איפה סיימנו בפעם שעברה. אין לנו אנשים בזום, אנחנו לבד היום, שזה יפה בינתיים פשוט. אז last time נכון, דיברנו על we talked about the Gelfand transform. So I remind you that the Gelfand transform is just homomorphism of algebras from the category of unital, commutative, Banach algebras to the continuous functions over compact output spaces. Specifically, it goes to the continuous functions over the Gelfand spectrum of A. Hey, Anton and Hannah, do you hear me well? Okay. So I'm just recalling what we did last time. And this was always contractive meaning increasing the norm less than homomorphism of a continuous, of course, of Banach algebras. But in the case that the Banach algebra happens to be the sister algebra, then we showed it is isomorphism of sister algebra. If A is a sister algebra, this is isomorphism. By the way, before we go back to sister algebras, an example I didn't give you last time, and maybe I should have, or I should do it now. So example for the Gelfand transform on just Banach algebras, one of the examples we had about Banach algebras that is not a sister algebra was L1 of a discrete group or the integers. I don't remember if let's say of the integers. So example, what is the Gelfand transform from L1 of the integers with convolution to continuous function over its Gelfand spectrum. So first, what is its Gelfand spectrum? Exercise, it is a circle. And what is the Gelfand transform? Well, let's think for a second. It's a homomorphism. So it's going to take convolutions of two functions, of two sequences to products. What is it going to be? It's going to be the Fourier transform. Okay. So Fourier transform is a special case of Gelfand. So example is Fourier transform. It's an easy exercise. I told you the answer right now, more or less. Okay, just you need to verify this spectrum, and once you know that convolution goes to multiplication, I mean, think about it. It's not hard to show. Must be. Okay, so but this is not in our world. Somehow we are in the sister algebra world. So we're not going to need such things. Only as counterexample, maybe. Anyway. So if A is a sister algebra, this is an isomorphism. And we met the following example. It's also last time. Example also from last time. took an element A in a system algebra A, which is normal, and we looked on a system of 1A. The smallest system algebra containing 1 and A. Since A is normal, it commutes with its star, so this thing has to be commutative. So by what we know, it has to be isomorphic to continuous functions on something, the Gelfand spectrum. But what is this something? What is the Gelfand spectrum? We showed last time, it's the spectrum of A with a small delicate issue, the spectrum of A where? In what sister algebra? In this. But don't worry, we're going to remove this issue now. But before doing so, just a remark. So this isomorphism, right? This isomorphism, this is just taking, this is just the Gelfand transform. Thank you. It takes A to A hat. A hat of phi is phi of A. But now, this guy here is homomorphic. I mean, okay. So this was the Gelfand transform of this sister algebra, right? But now here we also have another isomorphism with continuous functions over the spectrum of A. So this is from precomposition that we did last time. This is what we did last time. Was to find this homomorphism between this guy and that guy. And if you'll check this one, you will see that A hat goes to Z. This is what I wanted to say. Thus, if you go from here to here, do it to polynomials. You can do it to polynomials, right? So P of Z will go to P of N. And so, since polynomials are dense due to the Stone-Weierstrass theorem, something, well, I know that if I take any approximation of a continuous function by polynomial, it will go to the limit, which I will call from now on f of it. Okay? So before I just wanted to call this map F, capital F sub A. Okay, but it was not important, the notation, because I intended anyway to leave it and forget about it and denote it like this. Also, this is an isometric isomorphism, meaning that the supremum of F over the spectrum, so the infinity norm, the right norm here, has to be equal to the norm of this element. Right? So you can always do this for normal elements, and this would be very helpful. This is sometimes called the continuous functional calculus. So if you ever hear the continuous functional calculus, that's the thing.
The norm there is just the norm of the Banach space.
This is called, that's the norm of the sister algebra. Yes, it's known as a balance. This is called the continuous linear function. Continuous, functional calculus. Functional calculus. Aha, we did this. Okay.
We have A a priori. We begin with A and we have the algebra.
No, here you don't need to know anything about A, capital A.
No, little.
Yes, this is something that you do locally on little a, but in a minute we will see that. I mean, where you take the spectrum is that.
The F is maximal.
This needed to be. Sorry, what? Say it again.
F gets a maximum on A.
On the spectrum of A? No, I was just saying that half. I don't know where it's going to be maximum. I mean, it's a function. It's going to have a supremum somewhere. Continuous function and maximum. It's going to have a maximum. I'm just saying this maximum is going to be the norm of this. This is what I'm saying.
Okay.
This is because everything here was isometric. Reserving the norm. Okay? Okay. So great. So the only thing we didn't do, and perhaps this caused the confusion, was to verify that this was the map from last time. But this was the map from last time. We can verify this.
So we showed with algebra, it's not necessarily conformal, right?
It's not necessarily conformal.
And you can have
It's right now there is no Hilbert space in the picture. I mean there is no notion of angles. Okay.
Except for C.
So, but
This is a complex number.
no,
What is this?
an element in this sister algebra. So that's sister algebra.
Okay.
It's not a complex number. You should think of it like this. Take a normal operator.
No, but F, you take a function
Yes.
and then you give it an argument. Why don't you get a number?
A is not a number. A is like an element in the sister algebra. So think about polynomial for a second. Suppose the polynomial is z squared. So here you get a squared. So if A was an operator, right? We said that the subalgebras of B of H are an example of sister algebras. So think about the following example. I give you one normal operator on B of H, and you can think about things like f of t, where f is a continuous function over the spectrum of this operation. Okay, so this is what you have.
So
yes.
what the right side hides is that if we have a multiplicative linear functional, then there exists like a unique lambda, which is a point in the spectrum of A, and this is the correspondence like
Exactly. Okay. Good. So how to get rid of B? How to get rid of, well, we call it B last time. I mean of this. I just want to say the spectrum of A. So theorem permanence. Suppose A is a subalgebra, a subsister algebra of B containing unit level. Sister algebras containing the unit, I mean the unit of B. So they show the same unit. Then the spectrum of A as an element of A is equal to the spectrum of A as an element of B for every A. Okay. So from now on, you can write the continuous functional calculus like this. You don't need to remember sister algebra, which is good. But before proving it, just, okay, let's, okay, first, one direction here is clear. Which direction? What?
Point in the B spectrum are in the contains the A spectrum.
Yes, so you're saying this. If I'm invertible in A, surely I'm invertible in B. So if I'm not invertible in B, I'm not invertible in A. So we always have a remark. One, always have this. I mean, even for Banachal. Even for Banachal. This is not a course about Banach algebras. This is not a course about Banach algebras, but let me tell you what happens in Banach algebras. In Banach algebras, the phenomenon is really cool, I think. So suppose I don't know, that's the spectrum with some of these guys also in the picture. Suppose that's the spectrum of an element in the big in the big sister algebra. So suppose, so in Banach algebra, in Banach algebra, we can be in the situation that this is the spectrum. Okay, I want to copy this picture twice, and we can make it easier. So we can be in the situation that this is the spectrum of an element in B, in the big sister algebra, but suddenly in the smaller sister algebra, it will look something like, I don't know, maybe this remains, but somehow this disappears and this disappears. So somehow it erases the interior something of. So if you wanted a concrete example, you remember disk algebra, right? The holomorphic functions on the open disk that are continuous on the closed disk. And we know that we can think of it as a sub-algebra of continuous functions over the circle, right? So now take here the element Z. Of course, Z is invertible on the circle, but clearly not invertible on the disk. As a holomorphic function. So, in fact, more than that, the spectrum of Z in the circle is, well, circle. I mean here. But the spectrum of it here will just be the closed disk. Here now I see that I wrote this right. No, that's the correct. Yes, we know that the spectrum of B is contained in the spectrum of A. This is why I'm going to write this. Right. So also here you see, I to move from here to here, I erase something. Okay, but we're not going to elaborate more on this phenomenon. We're just going to prove that this will never be the case in sister algebra. In sister algebra, we always have the same spectrum. So let me erase this part. And
the point here is that the disk algebra isn't the sub-sister algebra of C of T.
It is not a sister algebra.
Yeah.
It is not sister algebra. It's just a Banach algebra. And in Banach algebra, we always have this containment. We need to show this containment, and we now know that this containment, somewhere we need to use the fact that this is a sister algebra because it's special to sister algebra. Okay. So let's start with an easy case. That element is normal. So let A be in A. Case 1, A is normal. So suppose that somehow there is lambda here, which is not here. No. So there is, suppose that there is lambda. I know that I want to show that this is contained here. So suppose that there is somebody that is here, not here, that is in sigma A of A minus sigma B of A. Okay. Then it is not in the spectrum of B, so there exists B in B such that A minus lambda times B is equal to B times A minus lambda, which is 1, right? It is invertible in B because it's in the spectrum. Great, so now we're going to do a trick that will help us to show that 1 is less than 0, or something like this. Define. So I want to. So suppose this is the spectrum of. Okay, so here is what I want to do. I want to define. And suppose this is the real part and the imaginary part. I want to define some function that will look like this. And then to cut it. So this will be something like 1. So here the middle of this is going to be lambda. And the function is going to be 1 minus z minus lambda. But I'm going to cut it somewhere here. And I need a height that is going to be the norm of B plus something. So choose your favorite positive number. And you will see in a minute why this is going to help us. So call this function f. So define f of z to be the maximum of 1 minus z minus lambda absolute value and norm of b plus 1. The minimum? Minimum. Of course, the minimum. And f is continuous on the whole plane, right? So now, let's see. So now, well, of course, this function, g of z, that is defined to be z minus lambda times f, is bounded by 1, right? And but for all, but lambda is in the spectrum of A. But lambda is in the spectrum of A in A. And f of lambda, what is f of lambda? F of lambda is going to be, it has to be norm of B plus 1, because here it will be infinity. So the minimum will take into norm of B plus 1. So the supremum or the maximum of f over the spectrum of A in A which we know that, so this will be the norm of B plus 1. But on the other hand, we defined in the beginning today that this is exactly what, by the continuous functional calculus, this is exactly f of A. Okay, so yes, so I did, okay. So let me assume in the beginning, yes, I need to add something. This is not what we showed today, but that's fine. We showed that this is true where A is the smallest sister algebra containing 1 in A. So case 1, even before the case 1, let me add here, without the use of generality, we may assume A is the sister algebra generated by 1 in A. Agree? If I prove it for this sister algebra, then I'm done because this is the smallest option. So now this is true due to the continuous functional calculus we defined today. But on the other hand, so now what is GA times B? No. So this is A minus lambda times f of A. Or I can write it like this, f of A times A minus lambda times B. Right? But what is A minus lambda times B? A minus lambda times B is 1. So this is nothing but f of A, which is equal to B plus 1. But on the other hand, this has to be less than the norm of B. But on the other hand, this is less than GA times B, which is less than the norm of B, because we said that G is bounded by 1. So also in the continuous functional calculus, it would be bounded by 1. Because it is isometric. So we got that 1 is less than 0, which is false. Okay? And you also see the how it is useful to use the continuous functional calculus. But we assume that A is normal. So case 2 is general. So here's the trick. Lemma A is invertible if and only if both A star A and A star invertible. Let's prove the lemma for a second. So one direction is clear. Which direction? Then clearly I can write, right? Then A star is also invertible, so the product of two invertibles is invertible. So this is clear. The other direction, but I think it is also clear. If A star A times B, if there exists B in A, well, let me write. Oh, I don't. If there exists B such that B times A star A is 1, and there exists C such that A star C is 1, then just change the parentheses, and you see with the inverse of A, the left inverse of A and the right inverse of A, right? So then this guy here has to be the left inverse of A, and A is left invertible, and this guy has to be the right inverse, left and right. It's enough to be both left and right invertible, right? Because you know the trick. If you're both left and right invertible, then you are invertible. Because B equals to B times 1. I mean, if B is one of the right inverse, B is equal to B times 1. Write this one as completely different. So just write hence. Okay, so let me go back to A general. So in case 2, by dilemma, 0 is in the spectrum, let's say A of A, if and only if 0 is in the spectrum A of A star A, and in the spectrum, and 0 is in the spectrum A of A star, right? But these are self-adjoint. These are self-adjoint because they are normal. So by the previous case, by the self-adjoint case, by the normal case, this is if and only if 0 is in the B spectrum of A star A, and 0 is in the B spectrum of A star. But this happens if and only if 0 is in the B spectrum of A, by the lemma. Hi, Tamar. Okay. So thus, right, you can do it also to lambda. Thus, lambda is in the spectrum of A if and only if 0 is in the spectrum of A minus lambda, if and only if 0 is in the spectrum B of A minus lambda, if and only Okay. Questions about this one? Okay. So now that we have the continuous functional calculus, and we know that we can work, we can do this in any sister algebras that contain our element. We can move to our next thing, which is star homomorphisms. These are the morphisms of category of sister algebra, star homomorphisms. So definition. Star homomorphism is a map phi from A to B that is every algebraic property. Are you have a question? That is every algebraic property you would ask from such a thing to be. So it needs to be algebraic homomorphism because there are algebra that is algebraic homomorphism. Namely, it's a linear map and it is multiplicative. And sister algebras also have stars. So I want it also to preserve star, to be, we call it self-adjoint. And self-adjoint. Self-adjoint. And that's it. Which is a weird definition because now you should ask, how come? What about the topological properties of the algebra? Probably want this map to be also continuous at least. Okay. So we will show it is continuous. Before that, maybe let me just also add that if both A and B are unital, both A and B are unital, and phi of one of A is one of B, then phi is called unital. So before showing it is continuous, let me do the quick lemma with you. Lemma. So if phi from HP is star homomorphism, by the way, in many courses of books of sister algebra that discuss polygon sister algebra, then these morphisms are sometimes called just homomorphisms without mentioning the star because they're homomorphisms of the category. But here we will have homomorphism later that will not necessarily be star preserved. So
okay, regardless of whether it's in one, it's always unital.
No. B can be non-unital, A can be non-unital.
No, say A and
Both can be.
the image of a unital algebra not necessarily unital.
No. think about, I don't know, the compact operators, which are unital, and I can send, can have the unital sister algebra C, which is complex numbers. I can send a complex number to one entry of right to some projections, some finite point projection in the compact operators. This will define a star homomorphism, but it will not be. We send the unit to some projection, not to one.
No, I'm not saying, but the image of
the image. Okay, so yes, the image. Okay, we'll speak about it. The image has to be unital. You're right. I mean, so what Jonathan said is that if this is unital, forget about B for a second. If it is unital or not, the image phi of A, which I don't know what is this object for a second. I mean, maybe it's not a sister algebra, maybe it's closed, maybe it's. But at least it has to be unital. This needs to be a unit of it, of course. Phi 1 times phi A. So lemma, if this is a star homomorphism, then for every A in A, then for every A in A, the spectrum of phi of A has to be in the spectrum of A. Why? If you are invertible, if lambda minus A is invertible, then clearly phi of lambda minus A is invertible. Phi of the inverse will be the inverse, right? Okay, if lambda is in the spectrum of A, so if lambda is so I'm showing. How do I show? If lambda is not in the spectrum of A, so this is if lambda is not in the spectrum of A, then there is B such that B times lambda minus A is 1. So phi of B times lambda minus phi of A is 1. So lambda is not in the spectrum.
Is a passive.
So it should be unital, yeah.
Okay, so unital. If phi is a unity star homomorphism. What happens if it is not unital? So okay, let's give it a
so it is the same but with the image, right?
Let's speak about this for 2 seconds. Notation first. Notation. If the sister algebra is not unital, we don't have the notion of a spectrum, right? Because spectrum is all the elements lambda such that lambda 1 minus A is not invertible. So notation, if A is non-unital, set the spectrum of an element A to be the spectrum of its side, the one-to-one integration. So from now on, we do this notion. And about the lemma, remark, if A is unital, then phi of 1 is a projection. projection, meaning that P star is equal to P and P square is equal to P, right? Because it is a star homomorphism. And in fact, phi takes A to P BP. This is a unital sister algebra with unit P. This is unital sister algebra with unit B, now phi is unit. And now phi is unit. So nothing will change. I mean, the theorem remains true. I mean, it doesn't matter that I think of the spectrum. I think of the right. This sits inside B. It's the same map. I mean, of course you can say maybe the range changes something, but we know it doesn't change anything that has to do with the spectrum. The fact that it is bigger. So this is in the case that A is unital and B is not. If A is not unital, I don't care about B. Define phi plus from A plus to B plus. So even if B is unital, I add another unit to B. And I define this map. And now this map is unital. So, and again, because we show the spectrum permanence, nothing, I mean, the theorem was true. Okay. So therefore, we can remove unitality. Okay, from now on, sometimes I will say that we can remove unitality in some assumption, or even I will write a theorem and we'll prove it for the unital case, and I will tell you this is similar to something we did before. It will be something similar to this thing. If there will be an issue, I will say it explicitly. Okay, so now a theorem. Let phi from A to B be maybe unital star homomorphism, maybe not. Let's see if I'm going to need it or more. Then phi is continuous. Continuous, and more than that, and in fact, phi of A norm is less than the norm of it, so it is contract. And I will need a lemma. So to prove, of course, the only thing I need to show is this part, right? Let's be continuous. Proof case one. A is self-adjoint, A is self-adjoint. Then phi of A is also self-adjoint, right? Because this is star map. Now, therefore, so the norm of A. Well, this is true for any normal element, has to be the spectral radius of it, right? Same goes to the norm of phi of A. So I want to show that this is less than or equal to this. So we need to show that this is less than or equal to this. So we need to show that rho of phi of A is in rho of this. But we showed, but by dilemma, the spectrum of phi of A is in spectrum of A. So we are done. This methodology. So I hope you think about the relation between the algebraic properties of a sister algebra and the norm structure, that they are related somehow due to the
This is just a desolation, right?
so they're related by calculations, right? Case 2, in general, well, okay, this is then phi of A is no, okay, but it will be difficult to show. Imaginary part, it's easier to do something like this. Phi of A, that is square, is phi of A star phi of A. Right, this is the sister identity, which is a phi of A star A. This is self-adjoint. It's positive, right? Self-adjoint. This is joint element. This is less than right. Okay. So did they use the fact that something here is unital? No, right? I didn't use the unit in this. Okay. So we directly proved it for M star of Sweden. So let me do another thing and then we take a break.
The notion of the spectrum is now was extended a bit.
Why?
What the spectrum is for a non-unitary.
For a non-unitary, yes. But I remind you that, well, since we have the spectrum permanence, the fact that if you have a sub-algebra that sits inside a sister algebra, then the spectrum with regard to the sister sub-algebra is equal to the. It makes sense to define things like this. I mean, you do no harm. If somebody takes another unitization, a big unitization, and tell me, no, this should be the definition of the spectrum of an element in a non-unitary sister algebra. But then, okay, go ahead. Of course, things are more dangerous with monochrome. Okay, but let's do just the following thing as well, and then it will be a good time to go for a break. So we show that any star homomorphism is contractive. Now let's show that every injective star homomorphism is isometric. So theorem, if phi is isometric, is injective, star is injective star homomorphism, then it is isometric. We're going to show. So I'm going to follow the same algorithm. Case A, to assume that phi is self-adjoint. And I'm going to prove something like this, but with equalities, not with inequalities. And case B here, but here we'll have equality due to case 1. So automatically we'll get case 2. Okay? So let me start with, let's do it reversely. Case 2, A general. A general. And use red star with equality instead of inequality. Case 1, A is 7. Okay, so we will show that the spectrum of phi of A is in fact the spectrum of A. So we always have one direction that we proved in the lemma. Which direction was it? This one, right? We always have this. We need to show the converse. So assume that this is not the case. Assume. So we want to show, right? We need to show this. Assume there is lambda that is in the spectrum of A, but is not in the spectrum of phi of A. So A is self-adjoint. Do you remember that we proved that for self-adjoint elements, the spectrum has to be real, right? And we showed it. The spectrum of a self-adjoint element is always real. So let me try to draw a picture. So here's the real line. Here is well, I know that the spectrum of phi of A lies inside the spectrum of A. So suppose this is the spectrum of phi of A. Right, this is the spectrum of phi of A. And this is the spectrum of A. This is the spectrum of A. And this is lambda. So I want to define a function, continuous function, on the spectrum of A, on the blue one, that will be non-trivial on lambda and trivial on the spectrum of phi of A. And then to use the continuous function of lambda. So I want to define something like this, right? I want to define some function that looks like this. So it goes to 0 before it enters. I don't know, maybe lambda is somewhere here, maybe it's somewhere in the middle, but I can always do this, right? This is a compact set. This is a point outside of the compact set. I can always do it. So pick a continuous function. Pick a continuous function f on the spectrum of A such that f of lambda is 1 and f restricted to the spectrum of phi of A is 0, then what's the problem? Then f of A by the continuous functional calculus is less than the supremum of f on the spectrum of A. That is well, no, I want to say it is equal to this, and this is greater than or equal to 1. Maybe I could make it exactly, but it's greater than or equal to 1. However, F, if you take supremum on the spectrum of phi of A, then by the continuous functional calculus, this will be f of phi of A. On the other hand, this is the supremum of this thing, which is 0, f is 0 in this set. So
very easy.
right. So phi of A is 0 because f is injective. So phi of A. Sorry, because what?
Phi is injective. Because of the phi is injective. And
Phi is injective, then what do I want to say?
You use the fact that lambda is real here?
No, the fact that I want to use that is a lemma that I didn't mention yet, and I guess I should have mentioned it before. So let's do it, and I'll write it officially in a minute. If you take a polynomial P and take a homomorphism, star homomorphism phi of the polynomial of A has to be the polynomial of phi of A. Because everything respects, because of the f phi is multiplicative and the additive, right, and the linear. So, and then it is continuous, so I can use the fact that Standardclass or ideas like this to show that, in fact, I can commute phi with any continuous function. So this is phi of f of A norm. So let me write here a remark, and later we will give it. Remark. Write this in a minute. Now you see that phi is not injective. So phi is not injective. Now just let me write the remark and take the break. Mark. I will also end another remark that I wanted to make last time and I didn't. And it's related. One, if P is a polynomial, then phi of P of A has to be P of phi of A. Thus, since phi is continuous, since it's continuous, for any f, continuous function, the spectrum of a normal, phi of f of a is f of phi. And also, just let me mention, because I don't think do you remember that we proved that the spectrum of a polynomial of an element is the polynomial of the spectrum of the element? Did I also say it is valid for any continuous function? Okay, if not, let me just say it. I'm just using the fact that I'm reminding something similar. Since P, since we showed that sigma P of A is sigma of A polynomials. In similar fashion. Yes, the reason I didn't mention this last time when maybe it was in the first spectrum in a continuous function spectrum. The reason I didn't mention it last time is because this was tricky before, right? Because the spectrum of f of a officially lives in the sister algebra generated by f of a, not by a. But now we know that we don't care. But this is true only from today. So that's the reason I thought to myself, okay, I'll do it later point. But we have it in our hands because we proved it for polynomials generally. Just approximated by continuous function. We approximate continuous functions by polynomials. Anyway, good, let's take it.
שאלה, טוב שאני שאלת בשביל אחרי זה בשיעור, תגיד, כאילו ברור שהספקטרום רציף או שיכול להיות?
לא רציף.
לא, יכול להיות מתוחכם, בלוחות חברים, אין בעיה. אני יודע שכל מה שכתבתי פה הוא פחות או בסדר, זאת אומרת, כל שהלמדה הזאת הייתה באמצע, אין בעיה. אני יודע שהוא קומפקטי, אני יודע שהספקטרום של האדום היה מוכל בכחול, ועדיין, יש לי נקודה מחוץ, נקודה... גם הוא קומפקטי? השתמשנו לא הוכחנו את זה בשיעור שאני ציינתי משפט פונקציונלית, שהספקטרום תמיד לא רק של כל איבר, כל האלגברה.
הטיעון הזה לא עובד גם אם הם לא ממשיים? או השתמשת בזה של למדה, כאילו של הספקטרום ממשי?
לא השתמשתי בזה של ספקטרום ממשי. אמרתי אין נורמל.
לא, זה הטיעון הזה.
הטיעון הזה, לבנות את הפונקציה F, אתה אומר לי שאם הייתי בונה אותה באופן כללי...
כי זה עדיין קבוצה קומפקטית.
כן, אבל...
זה את הטריק של הסלף הג'וינט.
הטריק הזה של הסלף הג'וינט הוא טוב ברמה כזאת שתשתמשו בו תמיד. בתור התחלה או בתור סיום, ואז כשהוא על סלף הג'וינט, ואז קל ממש לצייר דברים אפילו, ברמה אפילו של הראש. אבל אתה צודק, הרבה פעמים אפשר לבוא להוכחה בדיעבד ולהגידה. כן.
זה משהו שתקן מנסות?
אל תלעבוד על זה. אני חושב שזה רמפים שלנו.
כן. מעביר שבוע במדרשה.
אתה רוצה שאני אגיד?
לא, אני אגיד, הכל בסדר. נשמור את הטובה הזאת במשהו אחר.
זה לא הייתה הצעה לטובה, זה היה הצעה ספציפית, רק לשבוע הבא.
אני חשבתי שהוא גם שינה את השם שלי. אני אתמול אמרת, אולי לא שינית, אני אלך לבדוק שנייה ב...
שאלתי אותך.
לא, נכון.
נו.
וידיתי, רק טוב.
רן אמר לי להגיע, אני לא יודע מה לעשות.
להגיע לאן?
אני מתפשע.
וואלה, עכשיו קיבלתי מייל שאישרו לי.
איך קיבלת מייל? וואלה, על שלך עבור מהר, כי הגשת האחרון. כנראה בזה, במחסני.
טוב מאוד.
משהו אחר.
נגלת מפורס.
מי שלח לך? מייל אוטומטי?
כן.
אבל זה לא מבין על זה.
כן.
אבל יש לי כך כזה. מה לא מצליח להתחשמל?
להתחשמל?
כן. אני לא יודע, זה נראה לי הנעלה.
מה, הידיעות בחדר? הידיעות בחדר זה בעיה.
הידיעות בחדר שוברות את המנתניה.
שלי קצת פה. זה טוב שזה גומי, זה אומר שאתה...
לא יודע מה טוב ומה לא טוב, אני...
שאם אתה תתפוס את זה... גיא, מתי ממשיכים?
שאלה על הפי פלוס שהוספת איבר, אז פשוט מוסיף איבר, פי כמו הפי הרגילה, והיא מעתיקה אותו לעוד איבר ב-B. אז B יכול לאבד את המבנה שלו כיוניטל סיסטר אלגברה, יכול פתאום להיות...
לא, לקחתי פי שמעבירה את A פלוס ל-B פלוס, שלא אמרתי בדיוק מה עושה, אבל היא כמובן שולחת את A ל-B כמו שפי לקחה, ואת האחד שהוספתי ל-A היא לוקחת לאחד שהוספתי ל-B.
אבל אם B היה מראש יוניטל.
אז עכשיו היחידה הקודמת, היא תהפוך להיות סתם פרוג'קשן, ותהיה יחידה חדשה. היחידה הקודמת היא כבר לא תהיה יחידה, כי היא לא תהיה יחידה עם היחידה החדשה, היא לא תפעל טריוויאלית בכפל עם היחידה החדשה. אבל זה לא מפריע לי, כי זה הרי שהספקטרום, לפי הרושם שהספקטרום של פי של A נוכל לספקטרום של A. כן, זה טריק כזה לדברים כאלה. האמת שאפילו ברמה הפילוסופית, אני חושב שבמשך תקופה ארוכה, לא היה ברור האם העניין הזה של ניטיזיישן זה טכניקליטי, או שיש בו תוכן. היום יודעים שיש בו המון תוכן, הרבה פעמים זה כן ציפות. זאת אומרת, הרבה פעמים אתה יכול להוכיח משהו, לא יודע, אלגברה ציפופה מיחידה, ולעבור להוכחה של אלגברה ציפופה בלי יחידה, זה סיפור, ממש יכולות להיות תופעות משונות שמתקיימות שם, שהן לא ראית אותן כשהייתה יחידה. אז אני חושב שהם מבינים שכן צריך להתייחס במשנה זהירות שעושים את זה, ונגיד לו משפטים כאלה קלאסיים, זה בטח לא מודד. אז מה הקשר שלכם? אתה מתמטיקה? איפה את? אצל מי?
אני שנה א'.
עד עכשיו מאסטר?
כן.
ואתה? שנה שנייה, אצל רן טסלר.
ואתה אני לא יודע מי.
אני אצל ואז קלארצ'ה. זה לא טוב.
כן. מה איתך את מי אתה? לא צרף לך. גם חדש? כן. ואתה?
צביקה. ממדמה.
מדמה. מה זה קוונטום קומפלקסיטי? ואתה אני לא.
אני חדש, כן.
בואו נעשה סקר. מי עשה אותו הראשון בעברית? מי בפתוחה? אתה הצבעת על תלת מלא.
חצי על הפתוחה.
חצי על הפתוחה. זה היה כמו חצי עצמה. בן גוריון?
יערי גם
אני יודע. בן גוריון, מה יש לך? טכניון?
לא, אני הייתי באוניברסיטת חיפה.
חיפה, חיפה.
כן.
עושים שם דברים. אתה מכיר את עמי?
איזה עמי?
עמי ויזילטר.
לא, הוא במתמטיקה בטח. עשיתי במדעי המחשב.
מחשב בחיפה?
אני לא חושב שיש אוניברסיטה בארץ שם במדעי המחשב.
אני אתחיל אבל סבבה?
זה ריאליים בחיפה זה הומנים.
לא, פשוט הטכניון זה ריאליים וזה יותר טוב. בדרך כלל. ואין שם הומנים, כן? אז זה האלטרנטיבה.
חשבתי שזה מה שמשלים את הטלפון.
אז אני רק אגזור את הסיום של מה שרציתי להגיד, שזה עוד כמה דברים, ואז נעבור ל-positive elements. סיימתי? עוד יותר?
אז רק שאלה, כל פעם שבסוף פה של ההוכחה לקחת פונקציה רציפה, קירבת אותה על ידי פולינומים, ואז התייחסת אליה כ-f של איבר באלגברה.
נכון. נכון, אמרנו שיש את האיזומטריה הזאת שהזכרנו אותה בתחילת השיעור, והיא מאפשרת באמת לעשות דברים שקשורים לקשורים.
זה פחות ברור איך לעשות את זה בהערה השנייה.
נכון, בהערה השנייה זה פחות ברור.
אבל זה כאילו בגדול אתה מזרק.
כן.
יותר מסובך, אבל אותו רעיון.
נכון, אותו. אני אפילו לא יודע אם אני אצטרך את ההערה השנייה. כן, אני אפילו לא יודע אם אני אצטרך אותה לכבוד. לא יודע, נתתי להעיר אותה עכשיו. כן, אז אתה יודע, אתה צודק. לגבי ההערה השנייה בואו נרשום כאן אקסרסייז. כי אתה צודק, יש פה קצת תוכן. כן. אוקיי, בסדר, טוב. מה עוד רציתי להגיד? אז רציתי להגיד עוד איזה דוגמא וחצי. אחד, זה לא יודעים אחד. רציתי להגיד את הדבר הבא, זה בדיוק. If P as okay as if he is not one-to-one, okay, in general, then carefully, זה לא קשור ל-one-to-one, אבל אם זה one-to-one זה טריוויאלי, then carefully is an ideal, a closed star invariant ideal of A. By the way, let me just mention that I think I will show you maybe next time that ideals are automatically star invariants. Those ideals are automatically star invariants, in fact. But anyway, if C is not one-to-one, then curl C, or even if it is, then curl C is yes, I done this.
C is a star homomorphism.
Yes, that field. From A to B, star homo. Then curl C is a closed invariant, star invariant. Okay, this is clear. So I have this map. So if I have this map phi that takes me from A to B, and I have this quotient map that goes to A mod curl phi, then there is a map here by Twitter. Next is the diagram. Now this phi twiddle will be one-to-one. So this phi twiddle will be one-to-one and isometric. In particular, In particular, the image of phi, in particular, phi twiddle defines an isomorphism into its image, which is the image of phi. So this shows that the image of phi has to be closed. So, and phi twiddle from n mod phi to its image, which is equal to the image of phi, is star, is a geometric star isomorphism. And therefore, yes, I mean, I can't write isometric, I can't write isometric star isomorphism because I want to say it's a sister algebra. Maybe I just want to say isometric isomorphism. I mean, I just want to say it's closed, so it is isometric isomorphism. Therefore, this is closed. Therefore, it is a sister algebra, therefore, this is morphism of sister algebra. It also was a star morphism, but this is something it's closed, and in particular, star. A sister. Okay, let's write this because this is a non-trivial fact. So theorem. I'm just writing this. So I want this to be written. And image, the image, star morphism is always C-star. This is a very good phenomenon, which is of course very unique to sister algebras. So if you want an example, counter example, then we mentioned that the Gelfand transform is the Fourier transform for little L1 of Z. So maybe note, this is unique. This is special. And the Gelfand transform from L1 of Z with convolution to the continuous function of its Gelfand spectrum, which is the circle, is clearly it can't be isomorphism, right? This is not a sister algebra. It can't be sister algebra. It is dense as a dense image. So you know that there are continuous functions on the circle that are not the Fourier transform of sequences. Give them once. Okay. So positive elements.
In the abelian case, this lemma is like saying that a continuous map through a compact Hausdorff space is a quotient map, right?
Right. Say it again. The continuous
map between compact Hausdorff spaces is a quotient map.
What do you mean by say is a quotient map?
In that, like a topologically a quotient map. Like the
No, I mean, so I mean, you can be in the situation where, let's say, I mean, this is somehow contravariant. I mean, like that Y is a closed subset of X. So you have this inclusion topologically, but the dual map here would be quotient. I mean, this is C of X. This is, I mean, the kernel of this map, is all the functions that vanishes in Y. So this is the quotient here it's contained. And yes, that's okay, maybe this. Okay, so positive elements. So definition. We say that an element NA is positive, and we denote it by A greater than or equal to 0, if A is self-adjoint and its spectrum is in the positive real part or the non-negative. So for our discussion, the 0 element is positive. Now, so it's not hard to see. In fact, you're going to prove it in a minute, that any positive element in a C-star algebra can be written as X star X. More than that. In fact, I can find another positive element, X, and show that A is X squared.
This is because the continuous function.
Right. That's the continuous function on calculus more or less. Apply square root of X. The problem is to show that any element of the form X star X is positive, and this was open for many years. So back then, I think that there was several notions of C-star algebra. There was B-star algebra and C-star algebra. Maybe more. One of them assumed that elements of that one of the abstract requirements is that every element of the form A star A is positive by assumption. But it took time to see the proof. I will show you the proof. There is a trick in the proof. Nothing. I mean, nothing that is immediate, but it's a trick. But once you know the trick, it's easy. Okay. So we will show that the elements of the form A star are positive, but the fact that any positive element can be written in this way is easy. And we start with this claim. So this is what Yari said. Positive elements have unique positive square roots. That is, every A greater than 0, there is B greater than 0, unique, such that this square root. This is just the continuous functional calculus. Well, maybe you need to say another word for uniqueness. Both continuous functional calculus tells us that square root of x is continuous on the spectrum red, right? Because it is positive interval, inside the positive interval. And verify. Okay, so complete this. It's easy. I mean, you take b to be square root of a. You check that b squared is a. This is because, be careful, but use the transform that we have. And uniqueness. Plus, before uniqueness, you need to show that b is positive. The square root of a is positive. So why is the square root of a is positive? Because
we have two of them in the functional calculus.
First, it's alpha joint because f is this function, f of x, is a self-adjoint function. So in the isomorphism, it will take us to a self-adjoint element. So it means that the square root of the star is the star of the square root, which is nothing in this case. And the square root of the spectrum is the spectrum of the square. Okay. So you know what, okay? Plus uniqueness plus, maybe before uniqueness plus verify and this positive. Okay, so this is claim. So now I'm starting to work, and it will take some time in the direction of showing that A star is positive. Also, we will do some lemmas that make sense anyway. We will need them for later use. So claim if A is self-adjoint, then A can be written as A plus minus A minus, where A plus A minus are positive, and A plus times A minus is equal to 0, which is equal to A minus times. Now writing, okay, so maybe a quick remark before we show this. Writing an element as the difference of two positive elements, at least if we have a unit, this is easy. How come? Do remark. If A is self-adjoint and A is unital, then I can always write A as write A plus its norm minus, or maybe I can write it like this, the norm of A plus A times the norm of A minus A over 2. Why is the spectrum of each of these elements is positive? Of course, each of them is self-adjoint, but why is it positive? Well, it's clear because lambda of right
The normal phase is not space. The radius is the spectrum.
the spectrum of the norm of A plus A is equal to the norm of A plus the spectrum of A. And this lies inside the interval means A. Right, so okay. I mean, what I just wanted to say, it's really easy. I don't need this claim. If all I want is to write a self-adjoint element as a difference of two positive elements, but here I require something else. I require that the product of them will be 0, and I also want this to be for any element without using the unit, because right here I do need the unit. Okay. What did you do?
Yes.
No,
Here there is one. And there isn't an easy way to bypass this difficulty of 1. It's not that I can say, okay, let's take a very big other number and an element in the system. Okay. The proof of the claim. So again, I'm going to use the continuous functional calculus. So I'm going to take this function. One of them is going to be, this is going to be one of the functions.
So first you use the fact that the A is self-adjoint and the spectrum lies in the real line.
Exactly. This would be g of x. So it's just diagonal. Okay, I'm not writing the formula. And now I'm going to use the fact that A is self-adjoint. So and take so let A plus be f of A minus be G of A. Then clearly f of A and G of A will be positive because they will take the spectrum of A, which is a positive interval, to I mean, sorry, it's not, the spectrum of A is not positive, it's real. Anyway, you see, f of R and G of R are both in 0 infinity, and f of A star will be f of A, and G of A star will be G of A. So they are positive, and clearly, right, A has to be A plus minus A minus. Right? Why? Because f of x minus g of x is just the function x, which in the functional calculus goes to A. Right? Because this is okay. You can, and clearly you can also have also this. Okay, claim. So let me maybe stop for a second. Is it okay, especially the new guys, but also the old ones, that I do this, that I skip details sometimes? I mean, sometimes it can be, if it's difficult for me, the details that I do it on the right. I try to do it. but if it's, I think it's trivial, then I leave it. But you can always ask me. I suppose you can always come to my office and if you have questions or whatever, or Zoom, email. Okay. The following, I mean, sometimes when people see in the first time the continuous functional calculus, then it's hard to believe that everything works. But just need to believe it. The following are equal for a self-adjoint element A. 1, A is positive. 2, A is equal to B squared from some B self-adjoint. 3, lambda minus A norm is less than or equal to lambda for some lambda greater than the norm of A. 4, the same as 3, but for every section.
Yeah, then unit time, right?
You say that in order to write 3 and 4, I need unit. So the 1 and 2 are going to be equivalent to the phenomenon. Well, we know 1 implies 2. Right? We can do it even better with the B positive. Why 2 implies 1? So if we know that we can write A as B squared for some B self-adjoint,
The spectrum is the
spectrum is positive. It implies 1 by the spectrum, because spectrum of B squared is the spectrum of B squared, which is in R of the square, which is in R squared. This is a very bad thing, which is in and of course it is self-adjoint. Let's do one. Well, we also know that. Okay, let's do 1 implies 4, maybe. 1 implies 4. So, let's take the function. So, okay, that's the picture. I have here. I'm doing 1 implies 4. So I know that A is positive. So the spectrum of A is somewhere here. And yes, it need not be continuous. Okay? But that's the spectrum of it. Now I take lambda that is greater than the norm of A. The norm of A needs to be this way. And I take lambda that is here. Right? Lambda that is greater than the norm of A. And now I want to consider 2 functions. One function is the function f of x is equal to x. And the other function is the function. Well, I don't know why I wrote the blue. Okay, maybe I don't need this one. Wait a second. See? But this is the important function. Lambda minus x. So let's see. So what do we have here? We have that. So lambda minus A. This is by the continuous functional calculus. Let's call it CFC for now. By the continuous functional calculus, this is just the supremum of the function G on the spectrum of A. But the supremum of the okay, yes, this is stupid. I don't really need the one. the supremum of the function g on the spectrum of A in the worst case scenario is lambda. So 4 implies 3 is immediate. So what I need to show is 3 implies 1. Implies 1. So 3 tell me that there exists a lambda. So let lambda greater than A be such that lambda minus A is greater than is less than or equal to lambda. Then so what's the situation? So lambda is greater than lambda minus A, which is the supremum of G of S, right? So let me write this like this: X over sigma of A lambda minus X. So that's the situation. Right now you don't know that the spectrum. You don't know that the spectrum is positive, but you have here some lambda. You have here the norm of A. I don't know. Maybe I know that's A self-adjoint, so maybe its spectrum lives somewhere here. This can be the spectrum of A. However, the largest distance between somebody in the spectrum of A and lambda is not more than lambda. So I can't have x's over here. So it means that the spectrum of A needs to be in the positive part of the real line. Of course, if you want to do it more formal, you can, but I hope this is clear from the picture. Yeah, you couldn't see it, so this is a bad class. I mean, I said, okay, we have this by assumption. This is just the supremum of this. I'm saying maybe the spectrum of A lives somewhere here also in the negative part. I only know that A is self-adjoint. But if there's an x that is over here, then x minus lambda minus x, will be greater than lambda. So if it's bounded by lambda, it means that I cannot have elements that are in the negative real part. So the spectrum needs to be in the positive.
But what you said, it's for a given lambda.
For a given lambda, I took a specific lambda over here that is greater than and satisfied inequality. And I showed that I cannot have x's that lies here in the spectrum.
Yeah, but if you take a given lambda,
yes,
then you can take some value between a 0 and I don't know, something like.
So again, if there is some very, very small x here, the distance between lambda and x will be lambda plus something. But it's less than lambda.
But where do you use that lambda as a greater value than A, than the norm of A?
What happens if lambda is here? I cannot use, right? Then lambda minus x is greater than lambda. So maybe I do have somebody that lies here. I use the fact that lambda is greater than or equal to the normal. Okay, you see it? Okay, again. What did I say? I said, if there is an x that is over here, then x minus lambda is greater than lambda. So it does not satisfy this. But if lambda was less than the norm of A, then maybe lambda was here, right? Then now it is possible to have lambda minus x be less than lambda. You're saying it can be. Sorry.
Maybe it should be n.
You're saying that maybe in the other side I can have somebody, right? Because maybe I can have something very tricky. Maybe lambda can be, yes, so you're saying this is true for any positive element? For any positive element. No, but I did use saying that I didn't use the fact that lambda is greater than V.
Where's the problem?
No, there is no problem. It's fine, but just said that I didn't use the fact that lambda is no greater than that lambda is greater than the normal fact.
But you did. You said it.
This interval, it's like negative.
No, but this is also lambda here. So you say maybe, if this is lambda,
the equality with the supremum won't be right.
Imagine lambda is very, very small, then you can get something very negative.
If lambda is very
if the norm of A is big and lambda is very small, then lambda minus something that's close to the norm of A will be very negative. So this inequality won't be correct.
This inequality won't be correct? You're saying this inequality doesn't make even sense for
lambda negative.
For lambda negative, yes, but why not lambda positive and less than the norm of A?
Then the equality
for
won't
lambda
be
positive. Yeah. Or you could find examples for very, very small lambda and big
if A is positive.
Big elements in the space. If A is positive.
If A is positive, but if A is not positive, then that's fine. It doesn't ruin the. Okay, no, I think that's fine. Yes. Yes. No, but again, if we're in the situation that we have a self-adjoint element that satisfies this for lambda, just for some lambda.
For lambda greater than 0.
Greater than 0.
So doesn't it already imply that there is 3? Something weaker than 3 implies 1.
I think yes, and this is what I'm trying to think. Whether it is correct that if I just write, but then, okay, let's think about it later. Okay, it doesn't ruin anything, right? But this is still well. Let's think if we can strengthening this. We can strengthen this implication. It's not. Important now because I will show you in fact what I want to get. I want to get the following claim. I want to show you that the set of a positive element is a cone. So theorem, if A and B greater than or equal to 0, then A plus B is greater than or equal to 0. Proof. Let alpha be greater than the norm of A, and beta be greater than the norm of B. then alpha minus A is less than or equal to alpha, and beta minus B is less than or equal to beta, and A plus B is less than or equal to alpha plus beta, and alpha plus beta minus A plus B is less than or equal to less C alpha plus beta. Right, so by 3 over 4, we get this. So here I used, this is by positivity of A and B, since A and B are positive, plus property 4. That's it. Also, if I multiply an element by a positive scalar, it is of course positive. What is not true is if I multiply two positive elements, I might get something that is not positive. So be careful. For exercise, find A and B greater than 0, such that AB is not greater than 0. More than this. Do this with B equal to A. So find an element that is positive, but its square is not positive. No, this is not possible. This is not possible. Sorry. No, I had something else in mind. Okay, I will tell you later what I had in mind. This is wrong. I had something else in mind. Okay, I will explain what I had in mind. So wait a second and then I'll explain. Right now, find A and B. No, let me elaborate more on this point. What's the problem I want to explain? The problem is not with positivity. The problem is more with the self-adjointness, right? AB star is going to be B star A star. If they are positive, then they are self-adjoint. This is BA, and this can't be AB unless you're in the commutative case, and then this is correct. This is AB unless C star AB is commutative. In which case, AB will be positive. Because it's really just the product of two positive functions. Okay. Yes. So yes, and why did I say that this is the only obstruction? I mean the self-adjointness. So why is this the only obstruction? Because Okay, there's something here that you don't know, but I have to say, but since the spectrum of AB, well, you remember that we can shift elements up to 0 in spectrum, right? So this will be equal to the spectrum. I'm not going to shift these two guys, but square root of B, A square root of B. Remember that we do have a square root of positive elements. We will later show that A is positive implies that x star A x is positive for every x. So this will always be positive. So this guy will always be in 0 infinity. Sorry, Ari. This guy I'm saying will always be in 0 infinity because it is of this form. But therefore, this guy will be always in 0 infinity up to 0. Doesn't matter. So this will have a positive spectrum always. The problem is that it might not be self-adjoint, and it will be self-adjoint exactly when A and B commutes. Okay, so I didn't intend to do it, but I mean we noted something like to some nice thing here, right? Okay. Let me end with partial order on the positive elements. On the positive elements, in general, we write A greater than B if A minus B is greater than or equal to 0, but usually I will use it only for A and B positive, although I can do it in general. The positive elements form a cone, and they are closed under star. And the multiplication with positive scalars. And the plus that you mentioned before. Lemma, for every A star A plus A star is positive. Let's move this quickly. I mean, this is very easy. Write A as x plus iy, x and y self-adjoint. Right, so you remember how to do it? X is A plus A star over 2. Then compute A star A plus A star is x plus x minus x star, so self-adjoint. So x minus iy, x plus iy plus x plus iy, x minus iy. So this is 2x squared plus y squared. The thing is that in the middle, because things x and y do not commute necessarily, then minus iyx will not cancel with ixy, but it will cancel with the guy over here because they are in reverse order. So things will cancel each other here and there, and this is clearly positive because yes, x squared is positive, y squared is positive, the sum is positive, multiplied by 2 equal. Sum. Yeah, so the remark I had in mind before that I wanted to mention, so maybe let me write it so I don't forget the remark. Find an example or exercise. Find an example for A, B, positive, such that A is less than or equal to B, but A squared is not less than or equal to B. This is what I mean. If A is 0, then of course this is. Now we're good to prove the theorem. And I remind you, this was a very big deal back then. A star A is always positive. And people finally could get rid of this weird assumption to assume that such elements are positive. So I'm going to write a trick. I mean, that's the trick. So B, which is equal to A star A, is clearly self-adjoint. Decompose B as B plus minus B minus in the fashion we explained before, with B plus B minus greater than 0 and B plus B minus is equal to 0. Okay? Here is the trick. Write x as A times the square root of B minus. So, what is minus x star x? Minus x star x is minus. Before proving anything, what do I want to show? I want to show that B minus is 0. You see it? To show that the A star A is positive, I want to show that B minus is 0. So minus x star x is minus square root of B minus A star A square root of B minus. But A star A is just B, and B is B plus minus B minus. So altogether, this is minus square root of B minus B plus minus B minus square root of B minus. But the first guy will vanish due to this fact. So you can think about why this is also true if I take your square root. You can think about the spectrum if you want. Since this is 0, then the spectrum is 0. Then also if I take the square root to this side, then this product has to be 0. Anyway, the guy with the B plus vanishes, and we get here minus B minus. We get here minus plus B minus. which is positive. So minus x star x is positive. This can be true, of course, but this is what we're going to prove, right? We also know. Yeah, that's true. Thanks.
You used to write that since b minus and b plus commute, then also square root of b minus commutes with b plus.
Sure, you can do this like this, but it's even easier than that. Even if they don't commute, think about the spectrum. But you're right. We also know from the previous lemma that x star x plus xx star is greater than 0. So if I take the sum of these guys, this is greater than 0, this is greater than 0. So x6 star is greater than 0. Okay, this is not exactly what I need to do. To show, but this is almost what I want to show. Thus, I write the spectrum of x star x, which is the spectrum of xx star, is positive. But this tells us that x star x, well, but the spectrum of minus x star x is also positive, but the spectrum of x star x is minus infinity, 0. So the spectrum of x star x must be 0. So x star x has to be 0. So b minus 0. So, I mean, this is, now that you see it, I mean, it's simple, right? It's a simple proof. It's weird that it will happen for a long time. We're done. Just let me check if I want to say anything else about this. Okay, there are a few more things that I want to mention, but so maybe I will mention them next time. Questions? Bye, Anton and Hannah.
Bye, thanks a lot.
Thank you.